Okay, guys. Uh, Today in my video, I will be breaking down my RSA Cipher program. Um, Before I run the program, I would like to give you a little overview of what a Caesar cipher is, what an RSA cipher is. Okay, imagine you and your friend wanted to pass secret notes in class. You agree on a simple secret. Every letter in your message will be shifted forward by a certain number of places in this alphabet. This is exactly what a Caesar cipher is. It's one of the oldest yet simplest types of ciphers known to man. Let's say your secret is 3. To encrypt a message, you would just shift every letter forward by 3 places. So an A becomes a D, B becomes an E, and C becomes an F, and so on. So a great analogy is that the Caesar cipher is like a toy decoder ring. There's only one secret, the shift number, and anyone who knows the secret can both lock, which is encrypt it, and unlock it, decrypt it, the message. As you can might guess, the Caesar cipher is an extremely easy program to break, and if you know what the shift is, it's quite easy to decode the message. But the other program I'm going to be showing to you today is the RSA Cipher. The RSA Cipher is a much more modern and powerful type of cipher. It kind of forms like the backbone of most security that we use in the internet today. So the RSA is an example of an asymmetric cryptography, also known as like a public key cryptography. Unlike with the Caesar cipher, it's with a single key. RSA uses two different keys. A public key that can be shared with anyone in the world. Its job is to encrypt the message. A private key. This key is kept completely secret by the owner. So its job is to decrypt slash unlock the messages that were locked with its public key. Uh, Here's the magic behind this. A message encrypted with public key can only be decrypted by the corresponding private key. Even if you have a public key, you cannot use it to figure out a private key or decrypt its message. So how does the RSA work? Maybe if we use an analogy, it might help. So imagine you have a mailbox, right? You give copies of your mailbox address to all your friends. This is like the public key. Anyone who wants to send you a secret letter can put it through the slot. The mailbox key, your private key, only you have the unique key that can open the mailbox and reads the letters inside. So if you have a friend that wants to send you a secret message, they use a public mailbox address to lock the message. Once it's locked, not even they can open it again. Only the person who can open it is you with your secret private key. So yeah. So, what is the math kind of behind this logic? I will go through an example, work through like a basic example, and show you how the math works. But basically, it comes down to a mathematical trick involving prime numbers. It's to create keys that the system picks two extremely large prime numbers and multiplies them together. The public key is based on this resulting large number, and the private key is based on the original prime number. The trick is that while it's easy for a computer to multiply two numbers together, it's incredibly difficult and time consuming to take the very large result and figure out which two prime numbers we use to create it, which is called factorization. So, yeah, for a computer to break a modern RSA key, you would have to try a factor that the number that is hundreds and hundreds of digits long that would take even the world's most powerful supercomputer thousands of years to solve. So, you have a lock that anyone can use to lock a box, but only you have the key to open it. The lock is your public key. You can share it with everyone. The key opens the lock is your private key, and you keep it a secret. Okay, let's choose two prime numbers. For step one. So let's start with two small prime numbers. First prime being 11. Sorry, first number being 3. Second prime being 11. Let's multiply them. What do we get? We get 33. So this number 33 will be part of both the public key and the private key, and it's called n. So to generate the rest of the key, we need a special number called Euler-Stoichern function, written as phi. So there's a formula to this. So you use the first prime number, 3, minus 1, and the second prime number, 11 minus 1. So 3 minus 1 is 10, 11, 3 minus 1 is 2, 11 minus 1 is 10, and you multiply them and you get 20. 20 is very important because it helps us pick a number that can lock messages and calculate one that can unlock them. So let's choose a public key, the encryption key. Now we need to pick a number that is less than 20 and does not share any common factors with 20 other than 1. Let's list some numbers that are less than 20 and check it. So 2, yes, it has a factor of 2. 3, no, doesn't have any factors with 20. 4, yes. 5, yes. 7, no. 8, yes. And obviously this continues on. So let's pick number 7. So now our public key is 7 and 33. This is the key that anyone can use to encrypt a message for you. Okay? But let's find a private key, the decryption key. We want a number that undoes 7 under mod 20. So we want a number that satisfies 7 multiplied by something, mod 20 equals 1. So if we were to check, okay, 7 times 1 is 7, 7 times 2 is 14, 7 times 3 is 21. So 21 mod 20 equals 1. So 3 is a modular inverse of 7 of mod 20. So that means the private key equals 333. So this is the secret key you keep hidden. You do not share this with anyone. It is used to decrypt the message. So let's encrypt a message. Let's say the message is the number 8, or it can be representative of a letter A or something else. Okay? To encrypt it, we use the public key 733. So encrypt it, it is 8 to the power of 7 mod 33. Let's break it down. So 8 to the power of 7, 8 times 8 is 64, 64 times 8 is 512, and so on. And then we get, because it's 8 to the power of 7, you get 2,097,152. So now that 2,097,152 mod 33 equals 2. So the encrypted message equals 2. You send 2 to your friend. You then encrypt the message for the next step. To decrypt the private key, you do 333. We encrypted the message to and raise it to the power of 3, which equals 8. Now 8 mod 33 equals 8. You get back the original message, 8. So if we had that 8 representative of a letter or something, that's how we figure it out. The public key, remember, some things to note is that the public key, if we were just to review, we picked a prime number, 3 and 11. We computed n, 3 times 11, which is 33. We computed phi, and then we got 20. We picked a public key, no common factors with 20, and the public key 733. We found the modular inverse, which is 7 times 3, which is 21. 21 mod 20 equals 1. So our private key, okay, we found that 3 is the important part to the private key. So 333. The encrypted message is 8 to the mod, 8 to the power 7. Remember, the message we wanted to send was 8 or some type of representative of that letter, of that number, which can be equivalent to a letter. So 8 to the power 7 mod 33 equals 2. So 2, you send 2. The decrypted message is 2 to the power of 3 mod 33 equals 8, and we got the number to be 8. So that is our message. And so yeah, obviously this RSA program is done with a much larger scale with larger prime numbers, and that is what my program is going to be doing. So yeah. Okay. So what happens when we run this program? So we have when we shift and we click enter, we get these 3 prompts. So what if you don't know what to do? Let's type in H. Okay, so what is the message it gives us? It tells us choose an S to start an encryption. Pick a Caesar cipher, simple shift by 3, or RSA cipher, number based, more secure. Okay, uh, I've been given some more information. Why don't we start it? So we click S, we type in the letter S, and then let's pick a cipher method. Let's pick one, Caesar cipher. Let's see how that works. So we enter a message. So can you help me? So it encrypts it. As we saw, when I explained earlier, the A letter is shifted by 3, right? So A is moved to D. So and so on. So it shifts every letter in that message to 3 spaces. So yeah, do you want to decrypt the message? Why don't we say yes? Let's let's decrypt it. Yes, and it says, "Can you help me?" Okay. Now, what if we inputted some wrong letter? Let's say A, we inputted. It'll tell us it's an invalid input. Okay, let's continue the program. Let's press S. Let's type in S. Okay, let's see how this RSA cipher works. You enter a message. Can you help me? And then, yeah, this is the encrypted message in numbers. Do you want to decrypt it? Yeah, why don't we? Uh, can you help me? Awesome. And that is how my program runs for the RSA Cipher. But if we want to exit the program, we just type in Q and you exit the program. Terminates. Okay, so this is the main part of my program. So I built the Caesar cipher first, and then I added the RSA cipher after. So when the end program is false, it'll initialize a boolean to control the main program loop. So while not in the end program, you get a list of options. So these are the different input options: start, help, quit, as we saw. So you have all the alphabets. So you're defining a string to contain all the lowercase alphabet letters. From these are like all the 26 alphabet letters. So you encrypt. So like you're initializing an empty string to store the encrypted message, and you're initializing uh, an empty string to store the decrypted messages. So you input a decision, right? Obviously, this is obviously case sensitive, so that's why I use the upper function to adjust the whatever letter you input to the capital S, whatever, if you choose the start option. So when you're choosing the start option, you're prompted with these two options. So these are the print statements. So it tells you choose the cipher method. So you enter your choice, you enter your input option. So the first option is 1, which is the Caesar cipher. It will tell you to encrypt, like encrypt something in the input a message in lowercase. So it'll take the length of the message. You run a for loop, and then you have 26 letters. So it looks at all the different position, and then here is the important part of this. You're shifting it by 3, and it is over modulus 26 because there's 26 letters. So it shifts the message to its new position, and then this is what now the new encrypted message is going to spit it out over here. Um, so on in this section, it'll give you an option. So do you want to decrypt the message? You can choose yes, and then it will revert back to the original message. So the decrypted message is this. It will print it out over here. If you choose to press N, if you type in N, it'll say the decryption is skipped. And then over here is the choice of starting the RSA cipher. So that's one of the options. So if you go back all the way up here, you choose the cipher method. You pick 1 for Caesar cipher or 2 for RSA cipher. So here, if you pick 2, you would enter the RSA cipher, and as you can see here, here's the rest of the input. So help, quit, and then you can and if you input a letter that's not part of the program, that's not an accepted letter within the program, it will say invalid input. So yeah, so yeah, that is the code for the Caesar cipher. Okay, so let's look at the RSA program. So this is the top half of my code. So yeah, so in this function, you define a function to compute the greatest common divisor of the two numbers using the Euclidean algorithm. So you continue the loop as long as b is not 0. You assign it a temporary variable. We do this because when we want to do work within a temporary variable, but we don't affect what the original number is to that variable. So that's why we use temporary variables. It is quite useful. So we update b to be the remainder of a divided by b. We update a to be the previous value of b, return their greatest common divisor, which is the final value of a. So then we, in the next function, we're defining a function to find if a number n is prime. So if obviously, if the number is less than 2, it's not prime by definition. So yeah, 1 cannot be prime. So then you return false. The numbers are less than 2 and are not prime. So then you initialize a counter, I starting at 2, the smallest prime number, loop while the square of I is less than or equal to n. Check if n is divisible by I, return false if n is uh, uh, divisible by I, so not prime. You increment I to check the next potential divisor, return true if no divisor were found, and n is prime. So in this function, we use the get small primes. I defined a list of pre-selected small prime numbers, and this is the index. I didn't really use a random prime integer number generator because I wanted to work through these problems, make sure it was encrypting and decrypting my messages correctly. So I wanted to use a pre-selected small prime numbers. So yeah, here this is the modular of inverse. I don't know if you remember what I talked about earlier about the inverse. Modular inverse. Define a function. So you define a function to compute the modular multiplicative inverse of e modulo phi. You initialize d, the modular inverse to 0. So you initialize x1, initialize x2, initialize y1. For the extended Euclidean algorithm, you assign temporary phi to phi. You store that variable of phi in, like I said, the temporary variable. You continue looping while e is greater than 0. Compute the quotient of temp phi divided by e. You update temp phi to e and e to the remainder of temp phi divided by e. You update x1, x2, update y1 and d for the extended Euclidean algorithm. Check if the computed inverse of d is negative. Add phi to the d to ensure a positive modular inverse. Return the modular inverse of d. So yeah. Next function is called the manual power function. It gives you the base, exponent, and the modular. So you define a function to be to compute the base, the power of the exponent, and you mod manually. You initialize the result to 1. You loop the exponent like a certain number of times to perform repeated multiplication. Yeah, and then you multiply the result by the base and take the modular mod in each iteration and return the final result of base to the exponent divisible by mod. So yeah. And then here is the converting the string to integer. So you define a function, convert it to string to a list of values, initialize an empty list to store the values, iterate through each character in the input string. Initialize each variable, value to store the character. So the character in C, which we have right here, and then you initialize the counter. You initialize a counter I for finding values. You loop through the possible values from 0 to 255. So yeah, well, I is less than 256. Check for the character value I matches C. Store the matching value. Exit the loop once the value is found. Increment I to check the next value. Append the value to the result list. Return the list of values. So then you define a function, convert a list of values back to the string. You initialize an empty string to store the result. You iterate through each number in the input list. Initialize a counter, I for finding the character. Loop through the possible values from 0 to 255. 255, yeah. And check if the current value matches the number. Append the corresponding character to the result string. Exit the loop once the character is found. Increment I to check the next value. Return the resulting string. And here we return result. So here we use the generate keys function. So we define a function to generate our RSA's public and private keys. So we're obviously here we're calling. We go to the small prime function. So which is back up. Small prime function up here, and we assign that to P, and then we assign here Q to get small primes for, and then so P is using an index of 1, get primes number for Q is using an index of 4. Here you're ensuring Q is different from P. If Q equals P, then you get a new prime number using index 6. You compute n as the product of P and Q. Compute Euler's Taussian function, phi n, which is the prime number minus 1 and the other prime number minus 1, which I've shown you before. You initialize a public exponent e to 3. Ensure e is a coprime with phi. GCD, the greatest common denominator, greatest common divisor must be 1. Increment e by 2 to keep it odd until GCD e to the phi equals 1. So you compute the private key d as a modular inverse of e, modular phi, return a tuple containing the public key and the private key. You then define a function to encrypt a message using RSA. You extract the public exponent e and modulus n from the public key. You convert that message string to a list of values. You initialize an empty list to store the encrypted values. You iterate through each value in the message, encrypt the value using m to the power e, modular n. You append the encrypted value to the cipher list, return the list of encrypted values. Then here you have the RSA decryption function. So you define a function to decrypt the cipher using RSA. You extract the private exponent d and modulus n from private keys. You initialize the empty list to store the encrypted values. You iterate through each encrypted value in the cipher. You decrypt the value using c to the power d, modular n. You append the decrypted value to the list, and you convert the list of values back to a string and return it. So yeah, this is the RSA part of my program, and then you go back down here, and then right here is the cipher choice for 2. So this calls the RSA cipher as we have up here. It looks at the public and private keys, and yeah. Okay, so let's look at a challenge I faced. So this was like one of my older versions of my Caesar cipher. So let's click start. Okay, so let me implement a message I want to encrypt. Help me. Okay, so let's decrypt it. And then you see the issue right here, right? It fills in that letter Z in the space. So the original message was help me, but um, instead of printing the help with the space and the me, it prints in the Z to fill that space. So what did I do to fix this issue? So in my Caesar Cipher implementation, I check if each character is lowercase using this specific line. So hold on, where is the line I check is if new message is in all the alphabets. Okay, so all the alphabets, right? And if the character is not in all the alphabets here, right, which contains the from A B C all the A to Z, right? I simply append like the character unchanged. So yeah, that's what the else block is for. I encrypt the message. I include the new message, right? So here I encrypt the message. That's where I create the variable. Encrypt the message. Includes all the alphabets and the new position, and then I create this else block. Encrypt the message plus equals new message, right? And the same logic applies to the decrypting. So display message is in all the alphabets, right? I obviously do the decryption, right? And then I have the else block over here where I decrypt the message. So yeah, I decrypt the message, the variable is created here, and I'm calling all the alphabets, right, with the new position. And yeah, and this is all within the else block, and that's how I got rid of that Z statement, right? So from coming, so if I were to quickly, let's see if I can run this. Start S1 help me, and then yes. Yep. See, everything is done. Uh, yeah. So yeah, that was the challenge I faced, and that's what I did to solve the issue.